Very good. Welcome to today's class. The purpose of the class is to study the main application of the method of maximum entropy to derive statistical mechanics, to derive the canonical formalism. And so let's just get going. Here we are. And so what I would like to do is we're going to maximize the Gibbs entropy, which is this function in phase space. It is implicit that there is a 1 there, which says that this is a relative entropy relative to underlying measure, which is uniform in phase space. The dz that appears here is the integral over 6n coordinates. Very good. We want to maximize this. The situation we want to tackle is that of thermal equilibrium. And so the constraints that apply here are that the expected value of the energy codifies the relevant information to this problem, and also that the probabilities are normalized. If I'm using a clever way to write an expected value is something like this. A clever way of writing this as an expected value is that, well, if you have a 1 here, the average or the expected value of 1 is 1. That's another way to write normalization. So although it is not necessary, we shall discretize this. It makes the formulas look a little bit simpler, but this is not really necessary. We're going to have cells in phase space of volume, well, like we have it here. And if you take the cell and you multiply by the actual probability of that cell, that's the probability of the microstate A. So we could call this the microstate A. And so under those circumstances, the entropy is going to be minus A, sum over the microstates, PA log PA, and the energy, the microstate energy, we're going to write it as EA. And this is going to be, of course, it's going to be the kinetic energy plus the potential energy of interactions and all of that. So a lot is hanging here in this energy. But we would like to make sure to keep track of the fact that it could also depend on external parameters, such as magnetic fields, electric fields, or even the volume of the system. So when we maximize, what we obtain is the Gibbs distribution, where the Lagrange multipliers associated to the normalization condition here can be all brought together into the partition function, and that's going to be something like this, which shows that the partition function is a function of the Lagrange multipliers and the parameters, the external parameters that may appear in the energy. That's the Lagrange multipliers that go with normalization. The Lagrange multipliers that go with the energy constraint, that's going to be the beta, and the beta is determined by requiring that the expected value of the energy be equal to E. So we're done. So what we would like to do now is take these equations and analyze them. The first thing we would like to do is compute the maximized entropy, compute the temperature, and all of that. So the way we would like to phrase all of that is that we want to find or establish the connection to thermodynamics. And what that means is that we would like to have a connection between, say, so if we put here the statistical mechanics and here we have the thermodynamics, we would like to establish a connection between the expected energy and the internal energy. We would like to also pursue the connection between the information entropy and the thermodynamic entropy, say the Clausius entropy. So the question is, how do we do that? We would like to establish the connection between the object that appears when you maximize an entropy imposing constraints, which is the Lagrange multiplier beta, and the object that appears in thermodynamics. We also want to figure out what is the analog of that energy exchange that we call work, of what we call the heat, and so on. So this is how we establish the connection between the mathematics, the mathematical model, the theoretical model, and the, let's call it, the experimental science. So let us start by calculating the connection between the Gibbs entropy that appears here, the maximized Gibbs entropy, which is something that we obtain by just substituting the Boltzmann distribution in the formula for the entropy. And so we have here something like this. The maximized entropy is going to be minus the sum of all those probabilities. And then here we're going to have the log of the probability. The log of the probability is the minus beta EA minus the log of Z. Here we have, so the minuses all cancel out, and here we have beta, and we have the sum of PA-EA. So this is going to be the expected value of the energy minus log Z, and which is a constant, and then we have the sum of the p's, and that's a 1. So the maximized information entropy is something like that. If we multiply by K on both sides, what we're going to have is what you might call the Gibbs entropy, which is K S max, which is K beta E minus log Z. Very good. To establish some kind of connection the potential connection, obviously we're going to go for something like this. The information is, when we multiply it by K, this is going to be the Gibbs entropy, and this is what corresponds to the Clausius entropy. Very good. Next, we're going to go for the correspondence between beta and T. So to do that, we borrow a formula from thermodynamics, or rather the idea from thermodynamics, and we say, what happens if you have the entropy, which was maximized subject to a constraint on the expected energy, and you change that constraint? What happens when you change this at constant volume? So what we're going to do here is we're going to do the dVE at constant volume of beta E plus log of Z, which you might remember is a function of beta and V. So let's just do it. We have the d beta dE. Oh yes, and I forgot the K, right? There is a K floating around here. So we're going to take the derivative of the beta, multiply by the E, then plus K beta dE, that's 1, plus K d log Z d. We're trying to take the derivative with respect to E. So I'm going to take the derivative here with respect to beta. And then the derivative of beta with respect to E. And what we see when we do that is that here we have E, and in this expression here we have minus E, so that this expression cancels that one, and we have the SG dE at constant volume is this quantity K beta. Now this already starts being an indication that we want to set beta equals to 1 over Kt, because if Sg, if the Gibbs entropy happens to be the thermodynamical entropy, and this is the internal energy, then this is the connection with temperature. But we do not know that yet. We have to proceed. Now, right now, we're just writing down the analogous formulas that we would have in thermodynamics. Next, we're going to make the big leap of Boltzmann. Boltzmann's main insight. If you have the expected value and you write it as an expected value, and you say this is the internal energy, so this is the assumption here. We're connecting the statistical quantities to the thermodynamical quantities. We can consider what happens when you do a small change in the constraint, and that comes about from doing a small change in the probabilities and a small change in the energy. So let me do first a small change in the energy. PA. And plus the small change in the probabilities. Now, what is this guy here? Well, the way to change the energy of the microstates is to change the external parameters. And in this particular case, it means you do the change of the energy of the microstates by changing the external parameter that here we called volume. And so what we have there then is that the what we have here is that this whole thing is the expected value. Okay, the small change is the derivative, and then I have to multiply it by the change in volume. So what we have here is what we would normally call work. In fact, there is something important to be said here. Normally, work is something then that we would write as the change in the energy. Take the expected value when you change the parameter. This is what we're going to identify with work, which in thermodynamics is going to be minus PVV. The idea being that is that if the change in volume is negative, you're squeezing the system and you are injecting energy into it. You're doing work on the system. So this whole thing here for a negative delta V, this whole thing is positive. So that the pressure is P, which we write as minus the EdV. So here we have yet another expression in which we make a connection between the microscopic description and the thermodynamical description. Note, however, there is no reference to collisions with the wall of the container. Now, there is nothing wrong with interpreting pressure as being due to the momentum transferred by molecules that impinge on the wall of the container. Except that once you have an expression that does not mention collisions, you can start conceiving of this formula for the pressure as being something that can be more general. In fact, if you're going to think of collisions with the walls of the container, then it's not clear how that would apply to, say, fields or all sorts of other systems. In this case, we can generalize this to, this is generalizable to continuous fields. And in fact, if you think about even the 0-point fluctuations of a quantum field, so classical or quantum, if you imagine that you have a quantum field in a container and you change the volume, then the wavelengths of even the zero mode, the 0-point fluctuations, the wavelengths of those modes is going to change, and that changes the energy. The negative pressure that arises when you just look at the 0-point fluctuations, this is the Casimir effect. When you have two metallic plates and they're very close together, the effect of the 0-point fluctuations of the electromagnetic field will make them attract each other. So this is something that is included in this expression, and has nothing to do with collisions of anybody with the walls. Next step in this kind of like matching between the statistical mechanics and the thermodynamics is to say, if this first piece here is work, then this second piece here must be heat. So heat. The delta Q, we can write it as the sum of the EA, the change in probability, and this is just the change in the energy minus the work. And for that, we can actually go ahead and try to write it out. So what we would like to do here is to say, look at the following expression, this expression here. One of the crucial things that appears here is that what we call heat has to do with a change in the energy that comes from changing the probabilities. But the entropy itself is something that is computed in terms of the probabilities. So changing the probabilities gives you heat, changing the probabilities gives you the change in energy. So what we would like to be able to do is calculate the change in entropy. And here it is, the entropy. And I'm going to divide by 1 over k so that I don't have to carry many of those k's floating around on the right hand side. The entropy was log z plus beta e. So we have these two expressions there. And let's just compute them. There's a delta SG. So we proceed. When we do the change in the log of z, we're going to have 1 over z, the sum of the partition function. This is the change in, this is going to be z. So now we want to figure out the change in this object here. The change in the exponential is the exponential itself multiplied by minus delta beta EA minus beta delta EA plus delta beta E plus beta delta E. When we look at this expression here, here we have a constant delta beta that we can pull out, and here we have the exponential divided by z, that's a probability. So here we have the probability of EA summed over, so this is the expected value, which is what we have there. So this piece here cancels that one, and so the remaining piece is going to be just that the change in the gives entropy is going to be k beta, and then there is going to be the delta E that comes from the last term minus the beta, and here we have the expected value of delta E minus the expected value of delta E, which happens to coincide with what we call here heat. This is the expected value, the change in the expected value minus the expected value of the change. So what we have is that delta SG is K beta delta Q. This is the expression to be compared with the change in the Clausius and entropy is 1 over T delta Q. So we see that we have already two indications that if we match the entropy, the Gibbs entropy, with the Clausius entropy, then K beta is 1 over T. The other one was back here. The rate of change of the Clausius entropy with respect to internal energy is K beta, which is 1 over T. So you see how the mathematical formalism of the maximum entropy method and the thermodynamic formulas match one by one. Let us proceed a little bit more. We can integrate. We can integrate both expressions. When we integrate the Gibbs formula, we get that while we're integrating my tablet is not responding. There. Sometimes this happens. There. That's it. There. When we integrate the Gibbs formula here, we integrate and we're going to get the difference in entropies. Very good. So we're going to get the difference. We integrate from A to B, from a state A to a state B, and we're going to get the difference equal the integral A, B, K, beta, delta, Q. Now, the interesting thing when we integrate here is that all of these states that we have here are maximum entropy states. Remember, this is the maximized entropy, right? So let me write that very carefully and just say this is this plus where all intermediate states are maximum entropy states. And on the Clausius side, when we integrate the Clausius version, we get something like this. Something very similar, except that here we have a reversible path, and that was meant to imply that all intermediate states are states of equilibrium. So here we can draw yet another parallel. So let us summarize what we have here. To summarize the whole description, a macro, this is the thermodynamic version, a macro state of thermal equilibrium is described by the distribution, the macro state distribution, the distribution of maximum entropy. So from now on, when we talk about the macro state and we talk about the distribution, we're going to mean the same thing. We just draw an identification between the two. The macro state in thermodynamics is a situation of equilibrium that is described by the macro variables, the energy, the entropy, right? The volume, the pressure. Well, in the statistical mechanics version, the macro state is a distribution that is obtained by maximizing an entropy. It depends on the entropy and the constraints, right? So it's exactly the same thing. So this is the first piece of the insight. The second piece of the insight is that the Gibbs entropy matches the Clausius entropy. And it is important to recognize that what enters here is the maximized entropy. Furthermore, the Lagrange multiplier in the statistical approach matches the inverse temperature. Now it's very it's a good idea to draw attention to this because this is a wonderful result. Usually, temperature is explained or defined in terms of the expected kinetic energy of a molecule, right? In 3 dimensions, 3/2 kT. But notice that this definition defined or interpreted, this definition is limited because it definitely does not apply to photons. Photons do not have a kinetic energy, right? Definitely it's not going to be 1/2 mv squared. It does not apply to relativistic particles. The fact that what enters here is the kinetic energy is really having to do with the fact that you have a degree of freedom, momentum that enters quadratically, and therefore that's what's going to give you, when you do the expected values, 3/2 1 over beta. The moment that you have relativistic particles, the energy is like mc squared times a factor of gamma minus 1 to do the kinetic energy. It doesn't give you this, so it just doesn't work. And definitely it doesn't apply to black holes or all sorts of other objects out there. So this temperature as being something defined in this way as the expected value of kinetic energy is too limited. On the other hand, if you just say temperature is 1 over beta, where beta is the Lagrange multiplier associated to an expected value constraint on the energy. This is of universal applicability. No exceptions are known. Very good. We can do a little bit more with the mathematical formalism. And so let me just quickly show you how that is done. For example, when we have what we call the first law, and we say that the change in energy is given by the amount of heat plus the amount of work, and here I'm just using entropy, knowing full well that from now on, when we talk about the maximized entropy, it's thermodynamic entropy and it's the Gibbs entropy, right? What this is telling you is that the energy is properly thought of in thermodynamics as being a function of the entropy and the volume. And it tells you things such as if you were to do the derivative of energy with respect to S here, the derivative of E with respect to S at constant V, this is going to be T. And if you do the derivative of energy at constant V, sorry, derivative of energy with respect to volume at constant S, that's minus the pressure. And you can do the same thing in a language of entropy. We can actually write that ds is equal to 1 over T dE, get the PdV onto the other side, plus P over T dV. And from here you get that the derivative of entropy with respect to energy at constant volume is 1 over T, which is the expression we had before, and the derivative of entropy with respect to volume at constant energy is equal to P over T. Now, clearly, once you have this expression here, everything else follows. You never need to remember any of these formulas, and that's the reason why I'm going over them, because you don't need to know them, you just need to know how to derive them as needed. And this kind of process, for example here, this is particularly useful, this expression, when you are considering processes at constant entropy. And why is that? It's because entropy is not that easy to control, right? So under those circumstances, the change in energy at constant entropy, no heat, is just work. Very good. Most processes, however, can be done either at constant entropy, adiabatic walls, or at constant temperature. So for processes at constant temperature, we would like to come up with yet another function in addition to E and S that allows us to do constant temperature effectively, and that is the free energy. Is a Legendre transform. So here we go, the free energy is equal to the energy, and we would like to, instead of having TdS, we would like to have SdT. So what we do here is we subtract Ts. Let's do it. The change in the free energy is going to be the change in the energy minus the change in Ts. The change in the energy is TdS, heat, plus work. Then we have the second term here. This is going to be delta T S minus T delta S. This guy cancels that, and so we have that the change in the free energy is going to be minus S delta T minus P delta V, which shows that the free energy is a function of temperature and volume. So in particular, at constant T, the free energy is the work. So this is why this is called free energy. It's the amount of work you can extract by when the system is undergoing a process at constant temperature. It's in contact with a heat reservoir. And you can also find out that dF dt at constant V is equal to the minus the entropy dF dV at constant T is minus the pressure. So you get all sorts of formulas coming from these things here. So all the formalism is there. Very good. Not only we have all the formalism and we have established all of these deep connections between thermodynamics and statistical mechanics. What we have in a certain sense is also explained why statistical mechanics, why thermodynamics works. Not only can we get the mathematical formalism, we can get a lot of conceptual advantages here. And that's what we're going to do in the second part of the class. See you then.